Welcome back to this channel. In today's video, we shall look at how angular and linear variables are related in rotational motion. Let's look at a disk that is spinning about its center. Let's say the direction of spin is counterclockwise, like that. Let's concentrate at a specific point that is located at the rim of that disk, as marked with a cross there. We shall represent the reference line as always by the dotted horizontal lines. Obviously, as the disk spins about that axis, the marked point here will also move. So at a later time, it may end up there. We know that the point has gone through an angular displacement. You can call that angular displacement theta. Let's assume the radius of this disk is capital R. If you note carefully, that point marked in red would also have traveled a linear distance equivalent to that. Let's call that distance S. So obviously S is measured in the unit of meters because it's a type of linear distance, and theta is measured in a unit of radians, which is a unit that we use to quantify angular distance or angular displacement. These two units are directly related to each other, and the way they are related is as follows. The linear distance, or the arc length S, equals the radius of that rotating disk times the angular distance, theta. As simple as that. We note again, in using this equation, theta must be quantified in the unit of radians, not degrees. Next, let's look at the concept of velocity. This disk is rotating counterclockwise, so we know that the angular velocity is coming out of the board. Each point, such as the one that marked in red, would also have its own tangential velocity. So this is a linear velocity, and this is the angular velocity. The direction of v is tangential to the rim at any point, like that. From our previous videos on motion, we know that v is quite simply ds dt, and omega is d theta dt. So rate of change of that angular distance with respect to time. What that means is, if we take the time derivative of that equation, the left-hand side would give you ds dt. And the right-hand side, since r, which is the radius of the disk, is constant, you can take that out of the derivative sign and move on to theta and write it as d theta dt. Now from here, we know ds dt is the tangential velocity, and d theta dt is that angular velocity, and this is how the two velocities are related. Let's check the units. We know the velocity unit is meter per second. The angular velocity has a unit of radian per second. However, there is radius, which is measured in the unit of meters. So you see the left-hand side and the right-hand side of this equation have the equal dimension. So as far as dimensions are concerned, radiant is silent. So the right-hand side also have the dimension of length over time, just like the left-hand side. Next, let's move on to acceleration. Let's assume the rotation of this disk is speeding up. So the angular acceleration has a direction that is also coming out of the board. Since the rotation is speeding up, the tangential velocities of that point will also increase in time. So that means there is a tangential acceleration involved. The points on the rim are accelerating linearly along the tangential direction. Such an acceleration can be expressed in terms of that tangential velocity as quite simply dv dt. This is from our previous video. Also, the angular acceleration can be expressed in terms of angular velocity as d omega dt. Taking the time derivative of this equation, the right-hand side, taking r to be constant, becomes r times d omega dt, which gives us the connection between the tangential acceleration a sub t as equals to radius of that disk times the angular acceleration of that disk. So this is the crucial equation involving acceleration. A point to note here, this is the tangential acceleration, namely acceleration in tangential directions. Because such points are part of a rotational motion, they are also subjected to radial acceleration. Remember the concept of a centripetal acceleration we talked about previously? The direction of that radial acceleration or centripetal acceleration is radially inward towards the center. Let's call that acceleration a radial. So this acceleration is fundamentally different than that, the tangential acceleration. So what is the expression for the radial acceleration? Well, we know it is equivalent to the tangential speed squared over the radius. And we have seen a few minutes ago that the tangential speed is quite simply equivalent to the radius of that disk times the angular speed. Substituting this in here, we get the radial acceleration of the centripetal acceleration equivalent to the square of the angular speed times the radius of that wheel. So the point is, it's important to differentiate the tangential acceleration from the radial acceleration. Both are linear accelerations. They are quantified in the unit of meter per second squared. However, it's important to note that the radially inward component of that acceleration, or what we call the centripetal acceleration, is present whenever the angular velocity of the body is not zero, or the angular speed is not zero. The tangential component of the acceleration, that is this one, is present whenever the angular acceleration is not zero. So you can see the difference between the two. Let's look at the following problem. Find the angular velocity, the radial acceleration, and the tangential acceleration of a spaceship taking a circular turn of radius 3,500 kilometers at a speed of 30,000 kilometers an hour. So let's do the angular velocity. Angular velocity in terms of the tangential speed is quite simply that tangential speed over the radius of that trajectory. So in this case, the tangential speed is 30,000 kilometers an hour. So let's change that into meter per second. So first change the kilometer to meter, multiply that by 1,000, and then divide that by 3,600. You do that because you want to change the hour to seconds. And then you multiply with the radius, which is 3,500 kilometers. So 3,500 times 1,000 in order to express the radius in meter. We stress again here the 3,600 comes from the fact that 1 hour contains 60 minutes and each minute contains 60 seconds. So 60 times 60 is 3,600. And when you do the calculation, you get 2.38 times 10 to the power minus 3 radian per second for the angular velocity. Part B, the radial acceleration, meaning the centripetal acceleration. In terms of omega, it is just omega squared times the radius of the trajectory. Now we know what omega is. It's 2.38 times 10 to the power minus 3, square that, times the radius, which is 3,500 kilometers. So you multiply that with 3,500 times 1,000 in order to convert that into meter. And the answer is 19.8 meter per second squared. Now part C, the tangential acceleration of spaceship. In a circular motion, when an object make a turn, let's say from here to there, with the same tangential speed, but its direction changes, that implies acceleration. But that acceleration is the radial acceleration that we have just calculated. That does not give rise to any tangential acceleration. So technically the tangential acceleration is 0 in this case. In other words, if you concentrate on point 1 and point 2, that is here, and ask what is happening to the tangential velocity. At point 1, the tangential velocity has a magnitude of vt and the direction is tangential to that circular trajectory. At point 2, the speed is still vt and the direction is still tangential to that circular trajectory, thus giving us a value of 0 meter per second squared for the tangential acceleration. That means the answer for part C is 0 meter per second squared. Problem 2. A wheel with radius 0.5 meters rotating at an angular speed of 180 rev per minute. Find its angular speed in radian per second. So let's do that first. 180 rev per minute means 180. Each rev has 2 pi radians, as we have discussed before in previous video, and each minute has 60 seconds. So that's going to give you an answer in radian per second. And the answer is 18.8 radian per second. Now, part B. What is the linear speed of a point on the rim of the wheel? So the linear speed of a point on the rim, we are talking about the tangential speed, which equals to the radius times the angular speed in radian per second. So the radius is 0.5 meter. Omega is from part A, 18.8. And that's going to give you 9.4 meter per second for that tangential speed. Part C. What constant angular acceleration in revs per minute squared will increase the angular speed to 800 rev per minute in 120 seconds? So the angular acceleration is given as the final angular speed minus the initial angular speed over the time interval. Now we are interested in calculating the angular acceleration in the unit of a rev per minute squared. So the final angular speed is given in terms of rev and minute, so that is 800. The initial angular speed in the same unit is 180, so that's going to give you rev per minute. The time interval is 120 seconds, so 120 seconds is exactly 2 minutes, so that divide by 2 minutes. And the answer is 310 rev per minute squared. And that solves the problem. Thank you for watching.